second session now, which is on spatial temporal scaling and coupling of landscape models. We've got two separate talks. The first one's the double act between co-organised Felix and Paula. So I think, is it 25 minutes?
Yes,
no.
That's right.
Be good.
Okay.
I'll be timing you.
Right. Okay. Yeah. We have. So thank you very much. Hope you've enjoyed the morning so far. So Paula and I, which can be talking about the issue of progress and research gaps in spatial temporal scaling and coupling of models to support landscape decisions. So I'm going to do the bit on scaling. So I think hopefully all of you will agree to some extent that scale is a fairly central issue in landscapes, in that we are dealing with things that we're trying to, that operate at different scales and that are affected by things at different scales. If you're walking through a landscape like this, you're interacting it with at a view shed. If you're a farmer managing a field, you're operating at a different scale. If you're dealing with water flowing through this landscape, you've got catchment scale process, and of course you have feedbacks between things operating at different scales. So that's one of the great challenges of working with landscapes, is these scale disconnects in various things operating at scales, different scales. I just thought I'd very briefly define what is meant by scale. Scale, everyone talks about scale and scale being a problem, but it means different things to different people. So I think there's kind of two broad categories, measurement scale and what we call phenomenological scale. Just very briefly define them. So by measurement scale, people often talk about extent and resolution. Extent is simply how big is your study? Is it Britain or is it a bit of Scotland? Smaller extent, larger extent. Resolution, which is often also referred to as grain size or granularity sometimes, is, are you dealing with big pixels or little pixels traditionally? Or are you dealing with, for example, local authorities? That could be your spatial resolution as well. And of course that's spatio-temporal. By phenomenological scale, what I mean is essentially that different processes interact spatially and temporally at different scales. So if you're a critter, for example, a bird, you might forage at quite a local scale, but you interact with a much wider landscape when you're talking about dispersal. Both are important for trying to figure out what, for management implications. Again, for people, there are different scales, whether you're doing your dog walk or you're doing your annual trip to the Peak District, you interact with that at different scales. Same goes for water or almost any process. And it's important, again, to point out that phenomenological scales of processes don't necessarily correspond to management scales, which of course is another scale as well. So that's what we mean about this. Scale is an issue for a number of reasons. I'm just going to go for a very, I'm going to focus particularly on something called the modifiable area unit problem, which is more about grain or spatial resolution, which essentially says that patterns and therefore processes observed at one scale will vary depending on the scale of observation, which affects your stats and your inference. It's a problem for one variable. It becomes even more problematic for trade-offs, which of course are inherent in landscapes. So here's a very simple example. So if we deal with this, if say we've run some kind of model at this fairly fine-grained resolution, we've got trade-offs. Every pixel is either farmland or forests. Complete trade-off. All you do, if you change it to a coarser resolution, you have synergies, win-wins. Every pixel has both forestry and agriculture within it. Nothing changes into what's fundamentally going on, but the results change completely depending on the resolution. That's an example of the MAUP. So given this issue of the MAUP, upscaling and downscaling, changing grain, is quite problematic, but we have to do it because we are dealing with things that operate at different scales. If we're dealing with trade-offs and synergies, we need to somehow harmonize and work across scales. So that's one of the things we've been grappling with here. I'm just going to talk a little bit about some of these issues. So one thing that's been pointed out by Lex Comber is that while there's issues of spatial scale, there are probably even more issues of temporal scale, which we've largely been ignoring because of a lack of data. That's beginning to change. The remote sensing community, we've got all of these next generation remote sensing products where we've got very large data sets, both spatially and temporally, quite high resolution, which the remote sensing community has been very good about, or parts of the remote sensing community, the cutting edge, are very good about turning into what are called data cubes. So harmonized data, very large harmonized data sets, spatially, temporally, which means then that maybe we can begin to think about some new methods for dealing with these things. So for example, stuff from the geophysics community, such as work that John Brunn has been talking about, dominant frequency state analysis, where you can disentangle spatio-temporal signals from noise in quite a systematic manner. So there are new tools, there are new opportunities that open up with these new data sets, as well as these new challenges. Similarly, Bill Coonan has talked in the first talk quite a lot about upscaling and about downscaling of biodiversity. So both are important. We downscale, as we often have coarse-grained data, say from citizen science, but we want to manage at a local scale. And we upscale because we have field experiments where we have a really good idea of what's going on, but we want to, how do you take that inference up? So Bill has pointed out that we actually do understand quite a bit about some of these relationships, power laws of various kinds between upscaling and downscaling. But again, during the conversations we've had here, some new stuff has come out. For example, Danny Williamson mentioned this idea of spatial fusion techniques such as Bayesian melding, where you actually don't explicitly define the scale, but rather use these methods which are used in air pollution, they've been around for a while, to use high resolution, high quality point data to inform quite poor quality but broad extent, broad area models. So this is done for SO2 concentrations in the US. So these sorts of conversations have started to happen. I think there are some real cool opportunities there. Another one which I'm particularly excited about is, I guess, feeding into Duncan's point about, well, can we develop some universal laws? Can we understand, are there things that always matter? Probably not, but maybe there are things that matter much of the time. Maybe there are things that matter at certain resolutions in certain periods of time for certain kinds of landscapes. We've just begun to explore this sort of thing. I think we've had some really interesting discussions about this. So what people are beginning to do now, this is work, that map at the top is work Laura Graham has done with me, where we're beginning to just think about the patterns, but rather systematically, where we say, well, across Europe, for a quite large space of environmental variables, where are those relationships scale invariant? Where do we not have to worry about going from fine grain to coarse grain? And where do we? As you can see, the light green area is the Northern European plain. There, the relationships are largely scale invariant for quite a lot of environmental variables, as you would expect. You can safely upscale because they're big landscapes. In the mountains, the dark green, that is not the case. But then the question is why? And what are the mathematics behind this? So there's some quite cool ideas have emerged. For example, can we link scale to movement? James Bullock has pointed out that actually movement is quite well understood mathematically in ecology. There are things like integral difference equations which link population dynamics to movement, at least in one vector, quite mathematically, quite elegantly. Scale and movement are inherently linked, as I just talked about before. There's different. One of the reasons we get scale effects is things move at different scales across the landscapes, including people. Can we take some of those mathematical ideas from movement ecology and give us a bit more of a science of scale? Can we use Roderick pointed out that we can use, there's something called maximum entropy modeling, which comes from physics, where you say, well, what are the minimum constraints that are needed to get an emergent product? For example, a frequency distribution of land cover types. Can we do that? How many variables do we need for Britain to get the land cover signal we have now? Can we bump that signal to give us a new land cover signal? So what are those minimum variables, if there is one? And can we take some of the ideas from the climate community, emergent constraints, which Peter and Chris Huntingford work on, Peter Cox and Chris Huntingford work on? Can we take some of that, does some of that apply to landscape decisions? Obviously landscapes are more complicated, has been pointed out by several people, but still, maybe some of those ideas, or elements of those ideas, can apply to elements of landscape decisions, to give us a bit more, a stronger theoretical basis to work on, or at least to know where we can go with theory, and where things are really just too complicated, or too idiosyncratic, or too local to work with. So I think yeah, it's been very exciting, and I think there's some cool new directions. I'll pass it to Paula from there on. So, here we are.
Hold it like this instead. Thank you. Just break all the technology. See if I can get it back in. Otherwise I'm holding it. Okay, we'll see if that holds. Okay, so thank you, Felix. So yeah, I'm going to talk more on model coupling. When might we need to couple models together? And why might we want to couple models together? So what I'm going to try and show is a few examples of when we don't want to ignore the complexity, whether the decision means that we need to capture either detailed cross-scale interactions or maybe detailed cross-sector interactions, and what might be the circumstances for the need to couple models. So if we're looking at cross-scale, we all know that there are global drivers that affect the UK landscape. As Duncan was saying, there is the talk of money. We are in an international trading situation, and we trade many commodities which we export from the UK and we import into the UK. We also sign up to many international policy agreements, such as the UN Framework Convention on Climate Change, the UN Convention on Biological Diversity, and we want to collectively meet our goals to those kind of conventions. But ultimately we need to implement either nationally or locally, so we have to understand how those international drivers affect our national drivers and then our local implementation. And part of that is this whole area of telecoupling. So actually we could solve a lot of our issues in the UK if we simply export our environmental footprint to elsewhere in the world. So if we actually start to import lots more commodities, that releases a huge pressure on the UK landscape from the need to grow our own food or other commodities. But actually this is not what the UK will want to do. We would rather, I think, be an exemplar to other countries for meeting some of the big environmental directives that we signed up for. So that might be one area why we need to couple models. Another is if we look across sectors, we know that landscapes consist of many different sectors and there are big systemic interactions between them. For example, between agriculture, which needs water, depending on what agriculture does in terms of fertilizers and pesticides and different management activities, that could have consequences for biodiversity, for example. And most of those sectors interact because they compete for a finite set of resources within the UK, and those are usually the resources of land and water. So I'm just going to give a quick couple of examples of both the cross-scale interactions, modelling studies that already exist, and the cross-sector interactions. So this is a new global initiative called FABLE, which is the Food, Agriculture, Biodiversity, Land Use and Energy Initiative. It's coordinated by the UN Sustainable Development Solutions Network and IASA, which is the International Institution of Applied Systems Analysis. What they are doing is getting country teams throughout the world. They currently have 18 country teams signed up, covering most of the G20 nations plus others. They all run common land use modelling tools, and because they are common and they've been downscaled from a global integrated assessment model, they are able to develop national pathways to meet a set of global targets. So for example, if we were trying to get to net zero CO2 emissions, they can collectively develop those pathways. They go into a linker tool that looks as if collectively, if each of those countries implement what they say in their pathways, will we meet the global targets? And by doing so, do we create an unbalance in global trade? So are we trying to meet our own national targets by exporting our problem to another country? And it goes through this skenathon component, which is a mixture of scenario and marathon, in that there's a number of iterations. So we're almost simulating the negotiation process. So if we don't initially meet the global targets, each country has to be more ambitious. But if we're meeting the targets by unintended consequences in other countries, we negotiate through our imports and exports to see if we can balance trade. So very quick example, this has only been going for about 18 months. There is a first report out. So this was a very, let me find the pointer, this is a very simple example where we just tried to hit two targets of net zero deforestation and net zero greenhouse gas emissions from agriculture and land use sectors. All of the countries went through 5 iterations and tried to get more and more ambitious to meet those two targets. In this first version of the Skenathon, we failed to meet both targets, even by being very ambitious. Although you can see we made great advances in decreasing deforestation and decreasing net greenhouse gas emissions. But this, I think, illustrated how difficult it was. So we went through a second Skenathon process, and then we had 6 targets, and we did actually manage to meet collectively 5 of them. So I think it's a co-learning and a capacity building exercise so that all the countries can learn about how to try and meet some of these global targets collectively. So what do we mean? What did that mean for the UK? So within our own model that we upload into this system, it will show us basically how we have done in our own, trying to meet net greenhouse gas, how we've done in terms of reducing greenhouse gas emissions. We did actually in this Skenathon get to net zero here around about 2045. But to do that, you see we've got very large new afforestation coming here. We have implemented the government guidelines called the Eat Well diet, which has a massive movement away from red meat. And it has, we've also implemented all of the high ambition out of the Climate Change Committee's land use report that came out at the end of last year. That leads to a massive reduction in pasture because our livestock sector ends up concentrated on good quality lowland pasture, releasing lots of land from the uplands. But this is only results at the national scale. What this needs to do is link to spatially explicit models, so you can actually see, okay, based on these assumptions, based on the link to the global trade, what does that mean in terms of where certain land use changes happen within the UK? And that's just on where the results are. If people want more, which is part of the Food and Land Use Coalition website. So in terms of the other reason why we might couple models, this is if we want to look across sectors. So traditionally, most of our modelling is we might have models of each of these individual sectors. We might change some of the inputs or policy levers into those sectors, and we would get a range of outputs. And we might then try to synthesize across those outputs of those individual models to try and understand some of the cross-sectoral interactions. Where coupling those models together helps is that we can actually start to represent the processes of how those sectors compete for land and how they compete for water. You can then play around with policy levers and have a look at what are the collective cross-sectoral impacts. And often you will find if you make decisions in a coupled system, there are unintended consequences or consequences that you don't expect if you had run each of those models independently. So to illustrate this, this is just an example of an integrated modelling platform done at the regional scale for Europe and Scotland, and we've discussed this and other ones during the programme. This particular platform integrates 10 models representing the 6 sectors of urban development, water resources, coastal and fluvial flooding, agriculture, forestry and biodiversity through a series of data passes between, in this case, emulators of process-based models to get a fast interactive system. So what is the difference of running a model coupled together versus if you ran each of those sectoral models individually? So what we did is we ran the 10 models independently with no interactions between them, and we ran them in a fully coupled system. So this shows for a series of indicators in the green colours, the light green and the dark green, you get more than a 50% difference in the magnitude of impact if you run those models in an integrated manner to if you run them in a standalone manner. The ones with the double-headed arrows show you actually get a different direction of change in your impact compared to if you ran them in a standalone manner. So if you were basing your decisions on the individual 10 sectoral models with some assumptions of those interactions, you could get a completely different direction of your policy effect to if you were running it in an integrated system. This also highlights the importance of understanding some of the model assumptions within these complex systems. So in this particular model, there is an assumption that urban development is always prioritized over any other development. So here you will see there is no difference whatsoever whether that model is run in a standalone mode or in an integrated mode. And you just need to be very aware of what the assumptions are within these complex modeling platforms. So that's just a little bit of an illustration of some of the potential benefits of working in this way and trying to tackle the complexity, but it's actually really difficult to do. And the reason it's difficult to do is because unless you have an awful lot of time and resources to reprogram all of those historic process-based models, which is pretty much impossible, then you've got to find other alternatives to link them together. And usually these models are all developed in different programming languages, they run on different platforms, and usually getting one model to talk to the next is not straightforward. It's not like the output from one model straightforward follows the input to another. So what we need is, as an ambition, and this is probably quite a long-term ambition, is some kind of configurable framework that could apply. These Lego boxes, this slide I should give credit to Gordon Blair, who was during our program, where each of these little Lego bricks would represent some kind of transfer function, statistical function, scaling function that would help us to link models, and that could be configurable. It could potentially exist within a virtual lab to help us both access the various tools that we need to make coupling of models earlier and to actually speed up their running time by having access to running those models within the elastic capacity of the cloud. So some of the final issue I wanted to raise in relation to coupling of models is, of course, we all know there is a huge cascade of uncertainty even with running one individual model, and as soon as you start to couple models together, that uncertainty can cascade through the modeling chain or the modeling system and become much, much larger. And even with individual models, we're not always very good at dealing with certain aspects of the modeling uncertainty. So we do recognize quite a lot of these, particularly things like the emission scenarios and climate model choice. I think people always tend to use more than one scenario, more than one climate model, but actually people rarely use more than one land use model, and they're rarely particularly aware of some of the initial conditions or the accuracy of the driving data, particularly in land use and land cover change data. So two quick illustrations. This came up in a presentation by Lex earlier in the opening workshop, where he was talking about the terrible accuracy of global land use, land cover data sets, and that we use these to drive our land cover, our land use change models. So here in these bottom graphs, you've got a spread of structural uncertainty from an intermodal comparison of 16 global and European integrated assessment models that model different categories of land use change under different scenarios for cropland, pasture and forest. Here they've all been scaled to a similar starting point, to a similar initial condition and a similar land cover data set, the FAO one here. But actually, if you take the initial conditions that they really run from, you've got this awful spread of model output, and during the early years of the system simulations, it's massively dominated by initial conditions and between how each of those models define a forest and a pasture, which is massively different between each of them. One other quick area on quantifying uncertainty. So we've had lots of discussions about possible ways maths and stats can help us with uncertainty quantification in all landscape models, and particularly in coupled systems. And this is just one area where we thought it would be useful to investigate more, which is whether when we start to quantify uncertainty through a coupled modelling framework, using, say, a Monte Carlo method that looks at sort of sampling the parameter space. This was 21 model inputs that were grouped into 4 contrasting socioeconomic scenarios. And then the question is, does that lead to convergence or divergence in your model outcomes? And in this particular study, actually, it led to a fairly constrained set of model outcomes for this particular indicator, food per capacity. Yeah, thank you very much. So the idea here is we need to look in much more detail at these systems and when can we constrain uncertainty and when may integrated models help lead to convergence rather than divergence. So my last slide, because Peter's looking at me anxiously there. So this comes from the wonderful work of art that's on the blackboard over there. So over the last 2 days, we have been brainstorming some of the research gaps in all of our different areas and topics that Felix introduced at the beginning. And that is the roadmap of research needs for coupling of models. And as you obviously can't read any of the wonderful highlights over there, I've just pulled out a few here, and I've just grouped them into 2 main categories. One on the toolbox, why? Because currently it's incredibly difficult to couple models. Projects go off and do it on their own in different ways, and you have to constantly reinvent the wheel. So we just need some help from the mathematical sciences, but also here really from the computer sciences and software engineers to help us develop a toolbox of these functions that help us couple models together, to provide a collaborative environment for us to work together. And by doing that, we might be able to couple models that we've been having difficulty to couple in the past. So in particular, agent-based models, how do we actually link models of human behavioral processes and institutional processes, which are essential for us to understand decision-making, with some of the biophysical and the economic models that we tend to do a little bit better now. And then there's a range around actually the technicalities, and some of these represent to uncertainty. Where does uncertainty matter? So can decision theory help us actually understand the value information within a chain of models? Can Bayesian methods help us with model uncertainty and understanding how we quantify uncertainty? The use of emulators to speed up the running of integrated models to actually fully explore the space of decisions and to start to look at actually the full propagation of all different types of uncertainties. And then ultimately, can we start to constrain that uncertainty? And here what we were trying to get to is that in sort of the climate system, it's common to have all these ensembles of complex climate system models or Earth system models. So I think it was Peter showed there were sort of 30 to 40 different model realizations of all the RCPs. We're nowhere near that with landscape models. But actually, if we've got a framework to help us, can we ultimately get to having that larger ensemble so we can better understand the uncertainty around them and better support and inform decisions? So, thank you.
Thank you.
Hang on.
Great. Thank you both. So I'll ask our secretary to come up. While he's coming up, it's Richard Barnes from the Woodland Trust. We've got a little time we can ask grill these two. Any questions for Paula or Felix? Yeah.
It's not a question so much as an observation. I don't want to focus it on one particular presentation, but one quite often sees approaches to this question, particularly around emissions, for example, posed in what I describe as a normative framework, and I'm using that in the social science term, like how much space per person should you have in a house. And the framework of thinking around this, if it's to be practically meaningful, is that the thing is done through regulation. The second observation I have is the use of the notion of a nation as a single object, or a single decision-making object. And I get myself into trouble for making observations which I believe to be true, which is quite often you hear the phrase that something is in the national interest, and I often observe there's no such thing as a national interest, especially in the United Kingdom. There are merely collections of domestic interests which from time to time find it convenient to have a national interest. Now, the reason I'm making that observation, for example, is if you took seriously that demand to move from all of this pasture, what you're really talking about is, if you do that by regulation, you've got to pass regulation to tell people they can't have McDonald's, and I think this is unlikely as a regulative approach. And the second observation is it doesn't get at any understanding of the myriad interactions of the business systems which have resulted in the pattern of landscape one has today. If you go out into landscape, UK landscape, and look at it and ask why does it look like it does, usually the answer is because of some economic consideration.
Yeah.
So I guess my challenge a bit is to how do you start to build into your equations and your models. I think I just remarked to Peter after Peter's presentation this morning, my question is what's F, the function, or the functional parameter? Have you sort of addressed that question? Because I have a feeling if we don't, you're going to remain in a normative space which produces a set of policy options that nobody can actually pursue.
Mm.
Now that's a sort of challenge. I'm not stating it's a fact, but it's not. I'm not trying to focus it on a particular presentation because I see it a lot.
Yeah, there's more economics in this one than
But
most.
that is my challenge.
Yeah, I'd let Paula.
So yeah, I mean, I could have shown another example. So where modelling tools are trying to support, for example, the new ELS scheme, or we're doing a similar modelling tool development for Welsh Government as they're trying to also work out actually how do you incentivise farmers to change land use. So some of those issues of incentives, and whether that's through a combination of a very strong regulatory floor with other payments or subsidies, is being considered, but we also are struggling with and trying to look for new approaches, because we know that not all farmers behave in an economically rational manner. So some will, and there is some segmentation data out that shows there are certain, but the data is not good enough for us to know actually which farmers are where and which are the types of behavioural attitudes. So there is certain agent-based modelling approaches we're trying to couple with some of the economic and biophysical modelling approaches to try and actually look at what are the sensitivities of the system and the likely uptake rates of different policy levers, so different incentives, or whether you need a top-down regulatory floor, and also what are the time lags, because we know from historic data that as soon as the incentives or subsidies come in, all farmers don't instantaneously take it up. It can take up to 20 years for some incentives to be taken up. So there is work, again, that tends to be much more the local implementation. You need to know what's going on at the farm holding level and the fields within that farm holding level, and it's matching that to the trade environment that they trade their goods and commodities in. And very much now with the modelling that we're doing to try and inform Brexit, we're also being asked that we have 4 countries that are all developing new schemes, and they will also be negotiating internally within the UK as well as externally with new trading partners. So there is a huge complexity, and we're not ignorant of it, but the modelling approaches are going in small steps to try and tackle different parts of that project, that problem at different scales. And I think the challenge is linking the really big issues with the sort of the local issues and actually what would happen on the ground in terms of uptake.
Yeah, I should say Brett Day's not here, but Ian Bateman and Brett Day have a model that's entirely based on the kind of economic paradigm, really. And we had lots of interesting discussions with Brett about what utility function means and valuation of system services, but it's deeply embedded in these models actually. And the issue for us is often how do you connect that to agent-based models, where there's less sense of a sort of economic rationality in it, and that's one of the challenges. One quick one here. I know we're running a bit late, but this is good.
Just to kind of extend on that comment, I actually think there's as well as a sort of downward view, there's also an upward view you need to take, because one possible policy decision that the government could make in order for people to keep their McDonald's and still do the same thing with pastures would be to import huge amounts of beef and export our problem elsewhere. So I think we really have to take a global level as well as a national level in order to inform our national policy making. If we want to be good citizens of the world as opposed to just exporting our
much easier to meet your targets if you do it.
It is, and so really quickly. So I mean, I was last week. There was a DEFRA family meeting on. Okay, what's the UK's position going to be on the new global biodiversity framework? So the negotiations and the Conference of Parties will happen next year. So there will be a new set of targets for biodiversity. And they are, for the first time, realising that they have to have targets that address the indirect drivers of change, so societal and political drivers that address things like unsustainable consumption, because actually they realise actually they're never going to bend the curve of biodiversity loss unless they actually look at the consumption side as well as all the other policy levers they've normally played with and haven't managed to meet any of their targets in the last 10 years.
Great, we better move on.